Alright guys, so this is lesson 2.7. We're going to do some integration with inverse that result in inverse trig functions. So let's go ahead and get started here. This notation's a little bit confusing, so let's kind of look at something maybe a little bit more familiar here. So first of all, let's just review some things. First of all, you guys remember that, you know, what is an inverse trig function? Well, if you have sine of an angle, and that tells you y, then arc sine looks like that, and it's where you plug in the y and you get the angle as an output. And another way that that can be written is like this. They mean the same thing. So these are what we call the inverse trig functions, and we learned how to find their derivatives. Okay, so if you wanted to find the derivative of arc sine, for instance, so let's say I had arc sine of x. I'm going to use x instead of y here. And you wanted to find the derivative of that with respect to x. There was a weird looking little formula that we used for that one, which looked like this, right? But as you know, we're working backwards. So in other words, today we're going to start with this, and what we're going to do is we're going to integrate that with respect to x, and that's going to give us our answer of arc sine. But of course we're going to always have our plus c. So that's about it. Now there's some differences here though, because we might end up having a different number right here, or maybe this will be slightly different. So because of that, you'll see some slight variations in the outcome here, but that's kind of our goal for today, is to learn how to integrate these expressions that result in inverse trig functions. So here's a review of everything we've talked about so before in Unit 1. So the derivative of arc sine was this. The derivative of arctangent was this. That was the one that didn't have a square root in the bottom, and it was plus instead. And then the derivative of arcsecant, that's the one that had the absolute value bars, and it had a square root, but the u and the 1 were opposite from what we had up here. Now, when you compare these things to these ones over here, when you compare the derivative of arc sine to arc cosine, they have the same answers. It's just that one's positive and one's negative. Same thing for arc, when you compare arc, the derivative of arctangent with the derivative of arc cotangent. Same answer, different signs. Same thing with arcsecant compared with arc cosecant. Same answer, different signs. So since they basically give you the same answer, they're just different signs, whenever we see a problem that ends up looking like one of these, we're not even going to worry about these. We're just going to integrate them so they look like this, and if they have a negative in front, we're just going to put a negative in the front. So we don't really need the right side when we're working backwards, and that's what this is all about here. So if you guys ever see an integral with a square root on the bottom, where you have a number first and then an x, that's going to be an arc sine. But you'll notice that the inside's a little bit weird. And that's because, like I said, instead of having a 1 here, you could have something else. And this formula kind of takes that into consideration. Okay? So the a that goes in the denominator is going to be the square root of whatever number's right there. Okay? And the square root of this is what's going to go right there. Now, if you ever see one that looks like this, where you have a x squared plus a number on the bottom, well, that's going to be an arctangent. But same thing applies, square root, put your fraction here, but something special happens with arctangent. You get a 1 over a in the front. So once again, whatever is here, you take the square root of it, and you put 1 over that number there. Okay? Last one. Interestingly, even though when you take the derivative, you should end up with an absolute value here, you don't have to have an absolute value there for this to work. So if you see one that looks like this, where you have an x on the outside, or actually I should say, whatever's here is the square root of this, right? And then you have some number here. That's going to be an arcsecant. And like the tangent, it has a 1 over a. But whenever you do the integration, you are going to take the absolute value of the x value here when you plug it in. Okay? And we'll leave it at that. But those are your formulas for the other ones. Now, you'll notice we don't have an arc cosecant one. And that's because the only difference would be is that this would have been negative to begin with. In which case we could have said arc cosecant if we wanted to. But all we're going to do is we're just going to say, okay, we'll ignore the negative, put it out here, make the whole, do the integral, and then make sure it's negative at the end. So if it's negative, we're not going to do an arc cosecant. We're just going to leave it as secant and put a negative in the front. Because arc cosecant and secant, they're pretty much the same. The only difference is that one's a negative, one's a positive. So let's go ahead and jump in and do one of these. So the first thing you need to do is you have to decide what pattern does this seem to fit. So as you can see, we have a 1 on the top. That's fine. Over. And then after that, we have a square root with a number in the front followed by an x squared. So let's backtrack a little bit and see which pattern that fits the best. Does that look like the top, the middle, or the bottom? Well, it's not the middle because it's a plus here. We don't want a plus, we want a minus. And it's not the bottom one because the bottom one, the x squared, comes first underneath the radical, and also there's an x out here. That doesn't apply. So what we're looking at here is we're looking at this one. So the answer is going to have this format when we integrate it. Okay? So let's go ahead and jump back to where we were then, and we'll do that. So if I were to integrate this, it's going to be arc sine, which we could write like that, and it's going to be x over a plus c. Okay? Now, what goes here is the square root of the second thing, and what goes here is the square root of the first thing. So if we take the square root of x squared, you get x, and if you take the square root of that, you get 2. And so the answer for this one is arc sine of x over 2 plus c. And that's it. So basically, you just have to identify which one it is, and then take the square roots of these pieces and plug them in. Okay? Let's go ahead and do another one here. What pattern does this one seem to be fitting? Well, it fits the arc secant one. The arc secant pattern looks something like this. You have 1 over a arc secant, absolute value of x over a, and then plus c. So we just need to figure out what x and a are. So first of all, for the a, it's the square root of this number. So the square root of 9 is a, which is 3, right? So a is 3, so that's going to go in 2 spots. The thing that goes up here on the top is the square root of this term. So we take the square root of x squared and we get x, and that's what's going to go on the top there in the absolute value bars. So there you go. So basically all you have to do is find out which pattern it matches best. You have to take square roots to figure out what the x's and a's are and just put them in the right spot. So pretty straightforward. Go ahead and try. Oh, actually, you know what? These are extra problems here. So I'm wondering if maybe I'll let you guys try one of these things on your own really quick before we get more weird about it. So here's what I want you guys to do. I want you guys to pause the video, and I want you guys to try this problem right here, number 1 only, not numbers 2 or 3, just number 1. Try that and see what you guys get. When you unpause the video, you'll see the solution. So as you guys can see, this one fit an arc tangent pattern. The square root of 4 is 2, so that's my a value, and it goes in this spot and this spot, and the square root of x squared is x, and that goes here. So those are the 3 blanks we had to fill in for the arc tangent pattern. All right, let's go ahead and take a look at some slight variations on this basic pattern here. So for number 1, if you had to pick one that it looks most like, wouldn't you say it looks a lot like an arc sine, right? But the problem is there's an 8 up here. But believe it or not, that 8 doesn't need to be a problem because it's just a constant. all we have to do is take that 8 and move it to the front. So if I do that, now it fits my pattern a little bit better for the arc sign. So here's how that's going to look. So we have 8 times, and then we're going to do our integral of this, which is arc sine. Arc sine of the square root of that over the square root of that plus c. So the 8 just kind of goes to the front and sits there. And just so you guys know, we don't need to write x over 1 because x over 1 is simple, can be simplified to just be x. Okay? Let's go ahead and take a look at this next one here. Okay? I think I'm going to modify this problem a little bit. Okay? I'm going to make this a negative. And I'm doing that because I just want you guys to be aware of the fact that anytime you have a negative here, regardless of whether it's a number like 3 or if it's just like a -1, what I want you guys to do if you ever have a negative is to take it out. Okay? So let's do that. So I'm going to take out a negative, but there's also a 3, so we'll take that out as well. Now, which pattern does this look like to you? It's still not quite right, but what pattern does it look most like? Well, since we have a plus with no square root, that's the arc tangent pattern, right? But the problem is that you're not supposed to have a number in the front of the x squared. It's just supposed to be x squared, right? So we can also factor that 2 out as well, but here's the trick with that one. If you want to take the 2 out of the bottom, then you need to take it out of both of these terms. So here's what I mean by that. So we don't like having these numbers here in front of the x squared, so if you can take that out, but when you do, you have to take it out of both terms like you're taking out a greatest common factor. And now that that's there, I don't like that sitting there still, so next what I can do is I can take that 2 out and put it underneath the -3. And now this is a much more friendly expression for doing my arctan. So basically what I did here was I took a -3 out of the top and I took a 2 out of the bottom. So I ended up getting -3 over 2 on the outside of my integral. Now on the inside I've got 1 over x squared plus 9. So I need a little more room to write, so I'm going to rewrite that. But I took a 3 out of the top, I took a 2 out of the bottom, and a negative as well. And the result was 1 over x squared plus 9. And now we can follow through with our arctan rule. So first of all, we have the -3/2, which comes from here, right? But we also have to do the arctangent rule here, right? So here we go. How do we do that? We do 1 over a arctangent of x over a plus c. And actually, the plus c, you could put it in parentheses. But to tell you the truth, I think what I'll do is I'll put it outside the parentheses. And that's okay for these c things. They don't have to be included. So I'll just put it out there. But here we go. So the a is the square root of 9, which is 3. That goes in those two spots there. And the square root of x squared is x. So there's that. Now, I have these two fractions which need to be multiplied together. So those 3's cancel and I'm left with -1/2 arctangent of x over 3 plus c. So the purpose of me giving you these two problems here on this slide is to show you what to do if you have extra constants. If you have an extra constant on the top, just pull it out. No big deal, it's 1, right? Which is what we did here as well. But you can also have an extra constant on the bottom, but when you do that, you have to take it out of both terms simultaneously. Okay? So let's go ahead and see if you guys can handle that. So for number 2, you guys have a negative here. We don't want that there. And we also have a 3. So you're going to want to take out a -3 on that one. And for this one here, you're going to want to take out a 5 And we don't like that 2 in front of the x. So you're going to take a 2 out of the entire bottom. So there's your little hints there for 2 and 3. But what I want you guys to do is pause the video, do numbers 2 and 3, and when you unpause the video, you'll see the solutions. Okay, so let's take a look at these. I've got the answers boxed up there at the bottom. So for number 2, the first thing was I took the negative and 3 out, just like I told you I was going to. Then I applied the arcsecant rule to this because it fits the arcsecant pattern. And basically this 1 over 1, you can ignore it because it's just 1. And when you multiply it by the negative 3, you're just left with negative 3. And then here you have absolute value of x over 1, which is just absolute value of x. Okay. For number 3, we take out our 5 on the top, but we can also take a 2 out of the bottom. So we're taking out 5 halves. Now when you take a 2 out of the bottom, that leaves you with 16 plus x squared. Now some of you guys might have been a little bothered by the order here, because with arctangent, I think the x squared usually comes first. But this is addition, so it doesn't really matter which one comes first. You're welcome with addition to flip things around. You can't do that with subtraction. But with addition, it doesn't matter what order they're in. Okay. So in this case, if you take the square root of 16, you get 4. So that's your a. Square root of x squared is your x there. And then multiplying the 5 times 1, 2 times 4, you get 5/8 arctangent of x over 4. All right. So let's go ahead and take a look at some other types of examples here. Now these problems are a little bit more challenging because they pull in the whole process of doing U substitution. All right, so I've titled this one More Than Just an X Squared. So when you guys look at this, look at the bottom. Every problem we've done so far has always had an x squared down there because that's what fits the pattern for what we're learning right now. Is they always have an x squared down there. But what if it's more than an x squared? What if it's like an x to the 4th? Or what if it's an x to the 6th or something like that, right? Well, I'll show you guys how to deal with that. So the trick is going to be to rewrite it as a square rather than as a 4th. So what would I put in here so that when I square it, I get this? What would I put in the parentheses so that when I square it, I get this? Well, the answer would be whatever the square root of that is. Okay, so let's go ahead and take a look at that real quick then. So if I put in here 2x squared, if I square that, don't you guys see that's just going to give me this? So all I've done is I've rewritten this thing so that it's written as a square instead. Okay, so that's the main step there. Is you want to rewrite. Matter of fact, I think I'm going to draw my arrow so that the arrow connects to that. You want to rewrite it as a square. That's the main thing. Okay, so now, once you've got that, we're going to go ahead and we're going to do U substitution. So I'm going to number my steps here, you guys, just so you know. We're going to do some U substitution. Okay, so let's do that. The first thing that you do when you do U substitution is you let your U equal whatever, right? Now in this case, the 1 in the parentheses is going to be my U. So my U is that new number I just created. B, we're going to find the derivative of U with respect to x. After that, we get the dx by itself. After that, we're going to go ahead and do our U substitution up here. So it's going to be integral 4x over U squared. So I'm replacing the 2x squared with U. And I'm going to replace the dx with du over 4x. And voila, The 4x's cancel, so if we rewrite it in simpler form, it looks like this. And now, once we've done that, it fits the tangent pattern. So before I go any further, I just want to review what we did. When you have something that kind of looks like it would be one of these inverse arc trig integrals, but you have more than just an x squared, you're going to rewrite that piece as a square, and then you're going to do u substitution. And once you're done, the result should look like a very basic and simple arc trig function, and that's arc tangent. So now we do the integral, okay? And since that's an arc tangent, we're going to have 1 over a. The square root of 1 is 1, so 1 over 1 is 1. Guess I'll just write it out. Arc tangent. Square root of that is u over a plus c. Step 4, we're going to simplify it and put the u back in. So that's just 1, so we don't really need it. This is just going to be u. Right? But instead of u, we're actually going to replace the u with what u equaled. U was equal to 2x squared. And there's our final answer. Okay? So when you have more than an x squared down there, rewrite it as a square, do u substitution, and then just make sure you put the u back in at the very end. Okay? Let's do another one. All right. So for this one, let's take a look at it and see what we can do. All right. So for this one, which one would I want to change? Which one do I not like right now? Well, the one that's in here is the one that I want to change. Because remember, the one under the square root is the one that I want to be a square, right? So I need to start by rewriting that as a square. So what would I write there so that it's a square? What would go in those parentheses so that it's a square? So basically, we would take the square root of this. The square root of 9 is 3, and the square root of x to the 6th is x to the 3rd. Okay, the next thing we would do is we would do our u substitution. My u is going to be what's in the parentheses there. Take the derivative, get the dx by itself, do the u substitution, what did I get there? 9x squared. So in this case, the 9 and the 4 don't cancel, but the x squareds do, so that's good news. And so now we have the following. I'm going to take the 4 and the 9 out because those are just constants, so we can pull those out. And now I've got 1 on the top over 3x cubed square root of u squared minus 4. Now you guys might notice something though. You guys see how there's a little bit of a problem here? We have an x in there still. Now here's the good news. For the problems I'm giving you today, this is fitting the arc secant pattern, and so it's because of that, this is always going to turn out this way. 3x cubed. I can just replace that with u right now. So I'm just going to go back and I'm going to erase this and I'm going to replace it with a u. So for the ones that fit the arc secant pattern, you're going to have to put the u in 2 spots. you're going to have to put it here, and you're also going to, well, let me show you over here. You're going to have to put it here, and you're going to have to put it here. Okay, so you end up with that. And now we have our nice little arc secant pattern. So it's going to be 4/9, 1 over A, arc secant of the absolute value over A, and then plus C. So my A is the square root of 4, which is 2. Square root of U, which is U. And then we can go ahead and simplify this a little bit. So the 2 here goes into the 4 twice. So now I have 2 over 9 arc secant of the absolute value of U, over 2 plus C. But once again, we don't leave the U there, right? We put in the place of the U what U equals. Oh, I'm putting the wrong symbol there, aren't I? Let me fix that. Just notice I put a 2 there for secant squared. That's wrong. It's arc secant, so it should be a little -1. All right. So this one, when you're doing U substitution with arc secants, it's a little bit confusing, but let's go ahead and review one more time. So when it seems to be fitting the inverse trig patterns, but you have more than just an x squared, you're going to convert the piece into a square instead, right? After that, you do U substitution. But whenever it fits the arc secant pattern, you're going to put that U in 2 places so that you get that arc secant pattern. Okay? After you simplify it, you end up with your final answer, no big deal. I have one more note, though, I want to tell you guys about. This is something you would want to write down in your notes so that you don't forget, because it's something that's easy to forget, but it could throw you for a loop on our next quiz, maybe, if you end up with a question that does this, because I've seen the quiz software that I use do this sometimes. Just review some basic math really quick here. You don't have to write this. Just pay attention for a minute. What is -2 squared? It's 4, right? What's 2 squared? It's also 4. So -2 squared is the same thing as +2 squared. But what about -3? Well, we could do -2 again. What about -2 cubed? Well, that's -8. What is +2 cubed? That's +8. Okay? So a -2 when you cube it is not the same thing as a +2 when you cube it. Okay? Now, that being the case, if you take the absolute value of this, it doesn't change the number, the answer, because whenever you have a -2 squared, that's 4. And we take the absolute value of 4, you just get 4. No big deal. But if you take the absolute value of this, you do get a different answer, right? Because that's -8, and the absolute value switches the sign. So here's my point that I'm trying to make for you guys here. When you have an odd power right here, these absolute value bars are necessary. You have to have them there. Because if you don't, you actually get a different answer. But let's just say you were doing a problem that looked like this. And let's say you ended up getting this instead. Well, since squaring something makes it positive anyway, the absolute value bars really don't matter. So technically, you could write your answer like this. Okay, so I just want you guys to be aware that if you have an odd number here, the absolute value bars are absolutely necessary. If you have an even number right here, they are not necessary. Okay, but anyway, that being said, I want you guys to practice doing U substitution when you have more than just an x squared. So here you guys go. Go ahead and try your student practice. Pause the video and then see what you guys get. Okay, so here's our solution. So for number 1 here, step 1 is to rewrite it so that instead of 25x to the fourth, you have it as a square, which is your u. And then when you do your u substitution, it would look like this. You would replace the 5x squared with u squared, with u, and then you replace the dx with du over 10x. And when you're all done with that, you have a nice simple arc sine function, which can be replaced with the u at the end to give us the final answer there. For this other one here, we're going to replace the 4x to the 10th with 2x to the 5th squared, which tells us our u. Then when you do your u substitution, you'll get this. You put the u in two spots. You put it here and here. So I end up with two u's there because this is one of our arc secant setups here. Next, we have the x to the fourths are going to cancel out. The 4 and the 10 are left over, so I just pull that out to the front there. And what we have left over here is just a nice simple arc secant pattern. The a is 1, so you have 1 over 1, arc secant of absolute value of u over 1. I reduce the 4/10ths to be 2/5. The u is 2x to the 5th. We don't need the over 1. And we must keep the absolute value bars because this is an odd power plus c. Okay? And that takes care of that. So those are how you do integrals that look like inverse trig functions in the end.